I am a historian, not a physicist, not a philosopher, so what I'm going to ask is a question that's a historical question, and it is a question that is deceivingly simple. It in fact hides layers of complication, and perhaps this is kicking at an open door with an audience like this. We know that asking when particles became indistinguishable is not just a matter of asking for a moment of discovery when these two conceptions of particles and indistinguishability came together, because the conceptions of particles and of indistinguishability were in flux, and they were interdependent from each other throughout the 20th century. It's relatively easy to determine moments in which the formal expressions of particle indistinguishability became clear and were formulated, and they have remained clear and stable since, but the exact meaning of those formal expressions is still an open foundational question, and we will hear about that in this symposium by others. Still, this does not mean that the historical question is useless. I think that it can still help to clarify what the conceptual framework of current foundational research is. So it seems that there is a sort of a standard explanation of particle indistinguishability in physics textbooks, at least at an elementary level, where indistinguishability is presented as a consequence of quantum mechanics. Here I have the example from Max Jammer's book, The Conceptual Development of Quantum Mechanics, where Jammer says that Heisenberg was the first to recognize the importance of the notion of light particles, even though the investigations about the nature of light particles has a long history of its own, but Heisenberg realized the importance of it for the new scheme of conceptions, that is for quantum mechanics, and then he kind of cursorily mentions Fermi, Dirac, and Bose-Einstein statistics that he says not only lent weight to the concept of light particles, but they also showed that these light particles may be indistinguishable, that is, may lose their identity, which is a conclusion which follows from the uncertainty relations. So there's this way of presenting particle indistinguishability, which is expressed by the quantum statistics as a consequence, as an inference from quantum mechanics. But this runs against the chronological order of the events, because the quantum statistics were formulated before the uncertainty relations supposedly undermine the possibility of keeping tracks of the individual particles and therefore justify particle indistinguishability. But in fact, the first of the two quantum statistics was formulated before the first formulations of quantum mechanics by over a year. There is another account that is found in the historical philosophical literature, which is that of a choice between two different models of particle indistinguishability. So I found the best expression of these in Mary Hesse's book, Models and Analogies in Science, where Hesse says that, in fact, quantum indistinguishability or particle indistinguishability, or the quantum model of particle indistinguishability, was not a consequence or an inference from quantum mechanics, but it was in fact a choice between two indistinguishability models of microphysical entities. One is the billiard balls model of particles that are indistinguishable but are re-identifiable, and the pounds, shillings, and pence model of entities, that is, entities that are not re-identifiable because they have no self-identity. the choice was made on the basis of the requirement of observability. We are unable to identify individual electrons, hence it is meaningless to speak of the self-identity of electrons, hence electrons are like pounds, shillings, and pence in a balance, and not like indistinguishable billiard balls, and hence they conform to Fermi-Dirac statistics. Hess was not trying to give a historical reconstruction of the history of quantum statistics or of the concept of quantum indistinguishability. She was arguing for the importance of modeling in theory construction, but nonetheless, this scenario from the historical point of view does not fare well, just as the previous idea of a logical inference. This is not what happened. In order to understand how quantum statistics was interpreted in terms of particle indistinguishability, we need to move beyond the idea of a logical inference or of a choice between two pre-existing models. We need a more flexible model, because this historically was a process that was gradual and even, and it was a process of gradually modifying and adapting the familiar conception of particles to a changing theoretical and experimental context. And if we, at least according to my analysis of the sources, we can see that the early interpretations of quantum statistics can be roughly classified into three types. One is the interpretation of the statistical interdependence of equal particles, or like particles, as Jammer calls them, which was presented and is still presented often as a loss of independence to stress the contrast with the so-called classical statistics, the Maxwell-Boltzmann statistics, in which instead particles are statistically independent. The other interpretation had to do with the symmetry of the quantum formalism under permutation of equal particles, or the permutation invariance of the formalism, or the exchangeability of equal particles. And it is interesting that of course, this symmetry under permutability also existed in, in pre-quantum mechanics models, but it was considered to be physically irrelevant. It became relevant in the early quantum theory of the ideal gas that was championed mainly by Max Planck, under the insistence that the entropy had to be an absolute function, that the absolute value of the entropy had to be physically significant, not just differences of entropy. It again gained much more relevance after the formulation of multi-particle quantum mechanics at the hands of Heisenberg and Dirac in 1926, where the permutation invariance of the formalism introduced exchange terms in the energy that then later on gave rise to the idea of exchange forces. And then there is another interpretation that was brought up quite early on, and it was brought up as a way of making sense of this statistical interdependence that seemed to defy the normal ways or the standard ways of understanding how particles interact and therefore they become interdependent. It is the non-individuality of particles interpretation, again expressed in a negative sense as a loss of individuality, to stress the fact that in the classical statistics, particles are supposed to be individuals. This is an interpretation that has a story of its own. It seems to have gained more and more importance over time, it runs into a raft of important philosophical problems having to do with individuality. So it seems to me that in fact a unified quantum indistinguishability interpretation for quantum statistics only was fully articulated after the Second World War. I cannot find it in the sources of the early period of quantum mechanics, and therefore it seems to me that if we can give an answer to that initial historical question, is that the particles became indistinguishable when they became modern particles. That is, when the field of modern elementary particles emerged from a very large number of important experimental and theoretical development that took place throughout the 1930s and the early 1940s. In terms of what kind of historical tool we can use to understand this kind of developments, as I said, it seems that we need a more flexible way of describing the physicist's theoretical practices. That goes beyond drawing inferences or choosing between pre-existing models, because what seems to have happened in this case, as in other cases, is that theorists, sort of manipulate the mathematical formalism in an open-ended way, using conceptual models and formalism together within changing theoretical and experimental context. And it's pretty clear that in this case, as in many other cases in quantum physics, it was the formalism, it was the theoretical formalism that played the leading role in this process of open-ended manipulation for theory construction. In the theoretical formalism, not only operationalized the physics conceptions, but also took them in directions that were unexpected. No one chose to make particles indistinguishable. No one decided the particles would have to be indistinguishable in the sense in which they are in quantum statistics. So it seems to me that's useful to think about the mathematical theoretical apparatus in a mathematized laboratory science, such as microphysics, as a theoretical technology. This is the language used by the historian Andrew Warwick, or as paper tools. This is a terminology that's been introduced by the historian and philosopher Ursula Klein. This means we need to take seriously the idea that the mathematical formalism is like material technology, analogous to the instruments of the experimenters, which means that they have meanings. These tools are loaded with meanings, they are dense with meanings, they are interpreted by the physicists who use them, who manipulate them. And the outcome of the manipulations, is a result of both the meanings that the physicists attribute to the formalism and the goals that they have, together with the technical constraints, the technical design, and the syntax of the formalism itself. And that is how theoretical manipulations can lead physicists in unexpected directions. The outcome of the manipulations is therefore shaped by and also shaping the goals of the physicists in a process of mutual shaping, if you want. So just to quote Ursula Klein, the emergence of new scientific objects and new scientific conceptions in the laboratory sciences is propelled and shaped by this dialectic of tools and goals. And it seems to me that if we use this idea, then there are two aspects or two features of the use of technology, or material technology, and mathematical technology that are very much in relief in the history of quantum statistics. And that's one is the interpretive flexibility of these tools, that is, they are open to different interpretations, and the other one is unintended consequences, that is, they lead in unexpected directions. I don't think I have to go over all the steps, and I would not have time to go over all the historical steps that led to the formulation of the quantum statistics, but perhaps it's worthwhile to remind us that what we today call Bose-Einstein statistics was first formulated as a method to derive Planck's radiation law by Satyendranath Bose in a manuscript that Bose sent to Albert Einstein, and that Einstein greatly appreciated as a great breakthrough, even though at first Einstein did not understand how Bose could possibly have arrived at the right result using the method that he used. And then it became clear shortly thereafter that, in fact, Bose had made a mistake. He had committed a slippage. There was in his procedure, he proceeded algorithmically applying or he thought he was applying the physical model of Einstein's light quanta to thermal radiation. And he thought he was applying the Maxwell-Boltzmann statistics to the light quanta, just in the same way as Planck and others were doing for the ideal gas, to derive a theory of quantum statistics of the ideal gas. But in the course of this procedure, Bose committed a serendipitous mistake. And Max Delbruck, the physicist, is the one who first wondered in a published article whether Bose-Einstein statistics was discovered by serendipity. But I say in serendipity is the property or the occurrence of findings by chance, something that one is not looking for. Bose found exactly what he was looking for, and no more than that. He was looking to derive Planck's radiation law from Einstein's model of light quanta, and he thought he had done precisely that. What happened there was a slippage, and it was a mismatch between his conceptual model and the application of the formulas. His mathematical procedure was identical to the one that Planck had used, but Planck was using a different conceptual model. So Einstein, as I said, at first did not understand where the essence, as he says in a letter to Paul Ehrenfest, where the essence of this method was and how it could lead to the right result. When he was coming from almost 20 years of frustrating attempts to make the light quanta make sense, and he and others had tried already repeatedly to derive, well, not Einstein, but others had tried repeatedly to derive Planck's radiation law from the model of light quanta, and they had not succeeded. But what Einstein understood is that the same procedure algorithmically could be applied to the ideal gas. And so he immediately came up with a paper in which he produced a new quantum theory of the ideal gas using Bose's method. Where does the interpretation, the first of the three partial interpretations of quantum statistics comes from? It comes from that circle or subset of statisticians, or physicists involved in statistical mechanics, and in particular in the application of statistical mechanics to the quantum gas and to the statistics of radiation, who almost immediately notified to Einstein that, are you sure that you want to proceed in this direction, because what you're doing is incorrect. So there is a letter by Otto Halpern, a Viennese physicist of Boltzmann's school, asking Einstein, pointing out that this procedure was incorrect. Einstein had apparently several conversations with Paul Ehrenfest, who reminded him that many others had tried, and it was, unequivocally and repeatedly demonstrated that if you apply statistical mechanics to a gas of light quanta, what you end up with is the empirically incorrect Wien's law, not Planck's law. And so Einstein, in response to this kind of criticisms, sort of kind of provoked by these criticisms, came up with this interpretation, which is really, a bold and admirable move because he kind of owned to the idea that the method did violate one of the fundamental principles of statistical mechanics, the principle of statistical independence of the microphysical entities, but that was no mistake. It was a new statistics. And so it was Einstein who invented a new statistics, and Einstein supported this with the idea of a deep running analogy between matter and radiation between particles, material particles and light quanta. In the second of his quantum gas papers, Einstein conducted a systematic comparison between the new statistics, the new quantum gas theory that he produced with Bose's method, and the existing quantum gas theory based on the Boltzmann distribution. What he found is that the new quantum gas theory did everything that a quantum gas theory was supposed to do, and at a high temperatures it agreed with the existing quantum gas theory, which made use of a factor of 1 over n factorial, where n is the number of particles, in order to obtain an extensive entropy function. This is what was championed by Max Planck, for example. But also Einstein was at this point able to demonstrate that the existing quantum gas theory with that 1 over n factorial factor for the statistical probability did not agree with Nernst's theorem at low temperatures, and therefore it sort of sabotaged Max Planck's idea of producing an absolute measure of the entropy. Interestingly, therefore, Einstein contrasted his new theory, which he interpreted as a statistical a new statistics of non-independent microphysical entities, to the existing quantum gas theory that was a theory that utilized this mathematical artifice, and that mathematical artifice of dividing the thermodynamic probability by 1 over n factorial was justified by Planck with the argument of the exchangeability symmetry. Einstein did not see the two interpretations, that of the exchangeability symmetry or permutation invariance of the formalism, and the non-independence interpretation as being in fact the same kind of interpretation, or being capable of converging to the same interpretation. He saw them as being opposite to each other, alternative to each other, and the same did Max Planck in his immediate response to Einstein. Max Planck agreed with Einstein perfectly on this point. He says now we have two possible statistics. One is the statistical theory that he was developing, which was based on the use of the 1 over n factorial factor to have extensive entropy, and that was based on the presupposition of exchangeability of the gas molecules, while the other one was the new statistics of non-independence of the particles. Schrödinger is the one who first was capable of seeing that if you take the argument of full exchangeability of the particles and apply it logically to its logical consequences, you end up with the new statistics that we now call of Bose-Einstein. The Bose-Einstein statistics. But again, so he saw that there was no contrast or no conflict between the two arguments, but they in fact amounted to the same argument. But however, this realization did not warm him up to the new statistics. He disliked it. He thought it was an unintelligible way of assigning statistical weights to the states of an assembly of microphysical entities. He agreed with Einstein that the only possible way of explaining it was to postulate some kind of mysterious interaction between the microphysical entities that destroyed their statistical independence. And so, in fact, Schrödinger, in order to get rid of this prospect of an unintelligible new kind of conception of particles, he produced what we can say is a new model of microphysical entities that was based on the idea of quantized ways in which the microphysical entities that constitute, for example, gas particles are just the quanta of the energy levels of a wave field. By his own admission, that's what led him to the formulation of wave mechanics. But what is not often noted is that he did this because he wanted to get rid of this idea of a new statistics. He considered it to be a sacrificium intellectus, that is, an intellectual sacrifice because it was unintelligible to him, his new model was meant to restore the old statistics of Maxwell and Boltzmann, the statistics of independent particles. So I will go quickly to the end of the story, or sort of provisional or partial end of the story as I see it. It seems to me that a new conception of particles that incorporated the idea of quantum indistinguishability, whatever that may mean, as a general interpretation of the statistical behavior of particles starts to be fully formulated only after the Second World War. That is when elementary particle physics or high energy physics was coming on its own as a new field, and we can say that Dirac's naming of the fermions and bosons in 1945, in the autumn of 1945, can be seen as sort of the inaugural ceremony of the birth of modern particle physics, because it's the moment in which there is no longer this contraposition between a model of corpuscles that need to be statistically independent unless they interact with each other, and a model based on some kind of quantization of a radiation field. And the old opposition between radiation and matter gets abolished with the new classification of particles, which is based on the principle of symmetry and antisymmetry of the wave functions, and that corresponds to this new classification of particles into fermions and bosons. Now, coming back to the choice between models, or the sort of rational reconstruction of all this process as the choice of the two models, where is the first appearance, where is the birth of the pounds, shillings, and the currency model that Mary has used I did not do a complete historical analysis of all the important events that occurred during the 1930s and early 1940s. The earliest occurrence that I can see as the origin of a model that I know of is Schrödinger's, unsurprisingly, Schrödinger's paper, What is an Elementary Particle, of 1950, where Schrödinger presents the three statistics, the classical statistics and the two quantum statistics, using three different models based on this sort of imaginary situation of having three schoolboys, Tommy, Dick, and Harry, who are to be given two rewards. And so what are the possible ways of distributing the two rewards to the three boys? It says there are three different kinds of rewards that will illustrate the three kinds of statistics. If the two rewards are two memorial coins, one portraying Newton, the other portraying Shakespeare, then there are 9 possible distributions of these coins to the three boys, and you have the classical statistics. If instead the two coins are just two regular coins, 2 shilling pieces, he calls them, which for our purposes we must regard as indivisible quantities, then you have 6 possible distributions, and that's the Bose-Einstein statistics. And if instead the two rewards are not coins or medals, but they are vacancies in the football team, in which only one vacancy can go to each of the boys, then you have 3 possible distributions, and that corresponds to Fermi-Dirac statistics. So it seems that the idea of a model opposed to the billiard ball models, the model of the shillings, might come from there. So I've come to the end of my time. Thank you for your attention.